So we're moving into section 4.2b now, and essentially we're just going to ramp up the complexity of these problems a little bit and look at some harder linear systems that, for examples that use linear systems. Most of these are going to have 3 variables and therefore be 3 by 3 systems. So here's an example. Let's read it. Suppose you find a bag of U.S. American Eagle half-ounce, quarter-ounce, and tenth-ounce gold coins. The half-ounce coins are valued at $285, the quarter-ounce coins at $150 each, and the tenth-ounce coins at $70 each. The bag contains a total of 58 coins with a total weight of 17 ounces and a total value of $10,065. How many gold coins of each type are there? So let's kind of identify the various types of information that we have here. We have a total number of coins. That's one piece of information. We have a total weight. It's another kind of piece of information we have. And we have a total value. Okay, so the reason I'm numbering these is just to classify them so you can sort of think about what are the different types of equations that we're going to have. Now, a little bit more about this. The weight information, we also know the weight information for each particular coin, right? Because we know half ounce, quarter ounce, and tenth ounce. We also have value information for each particular coin. All this, 150, 285, and so forth. As far as the total number of coins, though, that one we don't know how many of each there are, and in fact that's the question, right? That's the main question. So let's define our variables. Let's let x be number of half ounce, y will be the number of quarter ounce, and z will be the number of tenth ounce coins. And this will help us set up our system. So I think I'm going to need the whiteboard. And my first equation that I'm going to write is this one right here, for just a total number of coins, because my variable is defined to be the number of each type of coin. I can just add those 3 variables together and get the total number of coins. So that's, to me, is the simplest equation to write. Then I can write an equation about weight, my other type of information, so we'll have a weight equation. And so what we know is the sum of the weights of each type of coin comes to be 17 ounces. We've got a total weight of 17 ounces, and then over here I need to have the weight of the half ounce plus the weight of the quarter ounce plus the weight of the tenth ounce. Now it's not just half plus a quarter plus a tenth, right? It's the weight of each individual coin times the number of coins. So each half ounce coin weighs a half an ounce, but there are X of them. Okay, and to that we'll add the weight of each quarter ounce times the Y of them that there are, plus the weight of each tenth ounce coin times the number Z. and that'll be our weight equation. And then finally, we'll have a value equation, which will look very similar to our weight equation. It's going to be value times variable. And our numbers are what? 285, 150, and 70. 285x plus 150y plus 70. Sorry, that's a 7. 70z, and our total value is 10,065. Okay, there's our system. Now from here, we can get the coefficient matrix, which is 1, 1, 1, 1 half, 1 fourth, 1 tenth, 285, 150, 70, and ultimately what we will do is take the inverse of that matrix and multiply it by 58, 17, $10,065. So that's going to be a 3 by 3, and this is going to be a 3 by 1. So at this point, we've got to enter the values into the calculator. And I'm going to have to change the size of my matrices. By the way, I always use A and B, but if you need to save one, you can go down and use matrix C or whatever. So it's a 3 by 3 matrix. 1, 1, 1, a half, a quarter, and a tenth. 285, 150, 285, 150, and 70. So there's our 3 by 3. Then 58, 17, 10065. Okay. And now we'll do our multiplication. Call it matrix A, invert it, and multiply it by matrix B. And that's it. So this is the number of each coin. We'll have 19 half ounce, 24 quarter ounce, and 15 tenth ounce coins. All right. So that one wasn't too bad. You see here we've got a 3 by 3 system. Let's look at another example. This one I think you'll find perhaps a bit more confusing, although it's still going to, it's still doable. So a commercial customer orders 50 gallons of a paint that consists of 35% red paint, 40% green paint, and 25% blue paint. The store will prepare the order by mixing 3 paint mixtures that are available in large quantities. A reddish paint, which has these proportions, a greenish paint with these proportions, and a bluish paint with these proportions. How many gallons of each are needed? Okay, so there's plenty of potential for confusion here. As always, the first thing that I'm going to do is kind of identify the question. So the question is how many gallons of each? And the thing that people mess up on these types of problems is they get confused about what is each. How many gallons of each what? So it's of the reddish, the greenish, and the bluish because we're mixing these paints to get the customer's order. So let's use RGB. R is going to be number of gallons of the reddish paint. This is number of gallons greenish. And finally, number of gallons of the bluish paint. All right. What types of information do we have? So in that other problem, it was pretty easy to say, oh, we've got value and weight and so forth. In this one, we just have a lot of different proportions. So we know that what we want is this. And then we have these proportions here. Okay. Now I can write a general total amount equation, which is R plus G plus B equals 50. Because I'm gonna, this is the number of gallons of reddish that I need to get the customer's order, and so on and so forth. So if I add all those together, I'll get 50 gallons. So I do have that equation I can write. In addition, I can also write I can write several equations. Let me list them. I can write a red equation. And so the red equation will be the red contributed by each paint. Okay. So the red contributed by each paint, and when I say each paint, I mean there is red in all of these mixtures. So let me go back to this problem. The greenish has red in it, the bluish has red in it. So we're going to say how much red is contributed by each of them. And then ultimately that needs to give us 35% of 50 to be pure red. So this is like when we did what was the example where we did the pure, it's like a mixture problem. We wrote, say for that methanol problem, we wrote a pure methanol equation. Now we just are going to have more than one pure stuff equation, and we have to have 3 equations at least. We have to have 3 equations exactly to solve for 3 variables. So we have 3 variables, so we need 3 equations. Okay, so our red equation, well, here are your red proportions. You can see them here. So we're going to, and this is RGB. So we're going to have 1/2 of the reddish paint, which is R, plus 1/6 from the greenish paint, plus 1/5 from the bluish paint. And together that's going to give me 0.35 of 50. Now it's really important that you think about this and understand why this equation works. I'm taking, every paint has red, green, and blue in it, and then I'm just selecting the red from each and adding them together, and it's got to give me the total red over here. And the total red over here is not 50, and it's not 0.35 or 35, it's 0.35 of 50. Alright, we'll finish this problem in the next video.